So I realized there was one more test that I'd like to do, and it's not really a demo but a test. And that is, what I want to do is measure the amount of current that our electrode over here can produce at about 20 kilovolts. So to do that, I'm going to make a very simple filter using a 1k ohm resistor and a 1 microfarad capacitor, and that will have a frequency cutoff of about 150 hertz or so. And I did a little bit of preliminary work and found a screw that I could use to attach our filter to the grounded chassis of our high voltage generator. And we'll take one of our wires that we've used for high voltage experiments and just loop it around the electrode over here and set it up so that we're certainly at a good arcing distance from our capacitor. And you might be wondering why I used a 1k ohm resistor, and it's because if I take a voltmeter, an expendable voltmeter, and hook the probes to it like this with a value of 1k ohms, what that will mean is for every milliamp of current that flows across the resistor, we're going to get 1 volt on our voltmeter. So just by looking at the volts reading here, we can see how many milliamps are flowing here. And the reason we have a capacitor here is to smooth out all the little bursts of audio frequency type energy from the static electricity device, which again are at about 15 kilohertz. So with a frequency cutoff of about 150 hertz or so, we should essentially just see DC on the voltmeter, and that will give us the average current flowing from here to ground. And by having this nicely grounded, this voltmeter won't get damaged, and if it does, well, it's a cheapo voltmeter, it's a nice one. It'd be too bad if it was damaged, but it wouldn't be the end of the world. So with that in mind, I'm going to fire up everything and we will see how much current flows. Oh, and I should point out one other thing. I did look at the rectifier, and the rectifier is rated at about 1 milliamp continuous or average and 50 milliamps peak. And if we assume that there's 20,000 volts on this at 1 milliamp, that's about 20 watts, which I think is a little bit less. So I'm going to guess we're probably going to see a milliamp or 2, maybe 3, maybe 4. But I really don't know, and I've never done this test before, so it's going to be interesting to find out. So on goes the power, and that was the isolation transformer firing up. And I'm going to plug in our high voltage generator into the variac, and now I'll turn it on and let's see what happens. Tubes are heating up. The oscilloscope shows the oscillator starting. And there we go. Oh, and look at that. I was quite reasonably right. We're getting somewhere around 2 milliamps. So that probably means the picture tube is being driven by about 40 watts of high voltage power. And I should actually point out that for color tubes, you typically have voltages more in the 25 to 35 kilovolt range, and probably higher currents as well. But that is a really interesting result. Actually, I'm just looking at this now. The current has sort of gone up to maybe 2.4 milliamps. So we're probably talking about 50 watts of power. Oh, it just went up even more. We're now at 3. You can certainly imagine that the light output of a black and white picture tube is somewhat less than maybe 60 watts. And exactly how much light is coming off the tube will really depend on how efficiently the electrons from the beam are utilized and how efficient the phosphors are at converting the energy from the electrons into photons. And as I'm talking, it's gone up even more, 3.5 milliamps, moving up to 4, perhaps. Yeah, 4. And it's continuing to go up. And maybe it's stabilizing at around there. So that's a very interesting result. And now we're hitting even. We're approaching 5, 4.45. Nah, it's leveling off at around there, and it's going down a bit. It probably actually varies too. If I change the voltage on the variac, it'll go down a bit because there's not very good voltage regulation. But there you go. So somewhere between 1 and 4 milliamps is what you'd expect to be driving an old black and white picture tube. There was one more thing that I wanted to show you before we take a look at how it works, and it just sort of dawned on me that many of you looking at this will never have seen the inside of a piece of 1950s, 1960s electronics. And you might be surprised to note that there is no printed circuit board at all. It's all point-to-point wiring. This would have all been done by hand by the workers at whatever plant made this TV. And the interesting thing is, although this is point-to-point, in that TV technician's journal that I looked at, a lot of the TV sets in 1962 did have printed circuit boards as opposed to point-to-point wiring. And what I sort of recall when I was fixing TVs in high school was that a lot of the ones that originated in Europe, typically made by Philips, had printed circuit boards, whereas a lot of the ones that were made in North America didn't. And my guess is what happened was North America was producing TV sets earlier and faster than the Europeans. And so they stuck with the technology that they had production lines set up to build. Whereas the Europeans, which got into the business a little bit later, were able to use more modern technology, including printed circuit boards. And hence we have the difference. The one interesting thing that I do remember is the high voltage section, which really is up here. In the European sets where this was on printed circuit boards, there was always a problem because these tubes would get rather hot, and over time the printed circuit board material around the bottom of the tubes would start to get brown and begin to char, and as soon as it did, the very high voltages that we found around here would start further charring and shorting through the charred printed circuit board material. And the fix was to scratch that away, file it away, and hopefully prevent the short from occurring. So for the very high voltage sections, sometimes the point-to-point actually was better, but for everything else, it really is amazing that the American and Canadian manufacturers were using this when, you know, it probably would have been, on a large production scale basis, cheaper to go to printed circuit boards. But they had their reasons. If you have a method that works, don't change it. Anyway, that's what the bottom of this thing looks like. A few things that I must have cobbled in, including the whole power supply section, which was not actually in this part of the chassis. So I just added it in over here. This is actually a capacitor that looks like it came from a German TV set or radio. So I was clearly scrounging parts, which is quite amusing. But anyway, there you have it. And now let's go see how it works. Okay, so let's take a look at how my high voltage generator works. And what I have here is the schematic from a TV that would have been very similar to the one that I hacked it out of. And I say very similar because unfortunately I couldn't find a model or chassis number anywhere on it, but what I could do was Google the 3 key tubes in the high voltage section, and I came up with a TV Technician's magazine from 1962 that had numerous different TVs all using these 3 tubes in very similar, if not identical, circuits. So I don't know if this is exactly the same circuit as the one that's in my high voltage generator, but it's very close, and I did use that to do some troubleshooting to try and figure out why the horizontal oscillator over here was not working properly. It's interesting. The same thing sort of applies today. Just like back then, where you got somebody making a set of tubes and providing a reference schematic, and all the consumer product makers essentially copying that with minor changes and packing it differently and selling it differently. The same thing happens today. When you buy something like a Wi-Fi router, chances are, even though different manufacturers have different branding and looks to their devices, a large number of them are actually identical inside with the same chipset and maybe just a little bit of different software where you configure the device. So same thing with old style TVs. Anyway, the bottom line is I want to show you how this circuit works. Now you can see that it is quite a complicated circuit, but we can actually distill that down to something that's really quite simple. And to do that, I'm going to draw you the circuit. So the basic circuit is something like this. We have a coil, and this coil is not the transformer that we've been looking at. It's not the flyback transformer. It's actually the vertical part of the deflection yoke in the TV set. And what the deflection yoke does is it moves the electron beam from left to right as the picture tube is scanning out the image, and then very quickly moves the electron beam from the right back to the left so it can start a new line. And here's how it does that. Start with being electron tubes. We're dealing with much higher voltages than we're used to these days, so maybe 150 volts DC rather than say 3 volts or 5 volts or something like that. And we have our tube, and if you don't know tubes, it might look like a very weird schematic item, but it's actually almost identical to a FET, which we would draw perhaps like this. or a NPN transistor. And we're only going to use this device as a switch, so it really doesn't matter which type of transistor we're saying it's equivalent to right now. Anyway, the bottom line is, what we would like to do is set up a current in this coil so that if this is our TV set screen, we have a gradually increasing current to move the electron beam across the screen, and then when it gets to the end, we need it to fly back very quickly so it can start the next line, and then repeat the process. And the position of the electron beam on the screen depends on the strength of the magnetic field, which is directly equivalent to the current flowing through this coil. So in fact, what we would like is a current through the coil that is gradually increasing to gradually move the electron beam across the screen, then very abruptly go back down to zero, and then gradually increase again like this, and so forth. And this would be called a sawtooth waveform. To do that, it's on a very simplistic basis, easy. And what we do is we drive our switch, be it an electron tube or a transistor, with a voltage that is on most of the time, and then for a very short time switches off, and then is on again, and then switches off for a very short time, and the process repeats. And what does this do? Well, when the voltage on the control grid or the gate or the base is high, the tube is on. So it actually shorts the bottom part of this coil to ground. And what happens when there is a constant voltage across a coil? We get a gradually increasing current through that coil. Exactly what we want. Now, we want to stop that current. That's easy. We just stop the voltage going to the control grid of the tube. We bring that down. The tube shuts off. This current stops. The magnetic field in the coil is forced to stop, and the electron beam suddenly moves very quickly to the left side of the screen. It flies back to the left side of the screen. Now you know where flyback came from. Now, that's all good and well, but there is a problem with that. And that is, when we turn off this tube, there is a lot of stored energy in this coil. And in an absolutely ideal world where things had no resistance and no losses, what you would end up having is an infinitely high voltage suddenly appearing here as this coil desperately tries to keep the current flowing. Which is another way of saying it desperately tries to keep its magnetic field intact. In the real world, there are various losses in the coil and so forth, and so that energy gets absorbed somewhat, but not completely. What inevitably happens is, when we turn off this tube, which was conducting, the output of the tube over here goes from 0 volts to when it was conducting to some incredibly high value, because this coil is now desperately trying to push current into the tube. And this is often at a voltage of something like 5,000 volts. And shortly thereafter, we turn on the tube. Tube conducts, this voltage goes back down to 0, and then at some point later on we turn the tube back off and we get another 5,000 volt spike and so forth. And this is not a connection here. Anyway, the interesting thing is we now are already beginning to see, hey, we might be able to do something with that 5,000 volts. But besides that 5,000 volts, the imperfections in everything that is absorbing all the energy in the coil unfortunately distorts this nice sawtooth waveform, and what we end up getting is ringing occurring. So the waveform looks something like this, which means the magnetic field also gets wobbly, which means that instead of scanning nicely across the screen at an even speed, we're in fact scanning quickly and then slowly and then quickly and then slowly, and what you end up getting is weird distortions on the image. So you have to get rid of this ringing. And way back in the early days of TV, what they realized they could do is put a resistor across the coil like that, and that would dampen this ringing and help produce a nice sawtooth waveform, and that's what they did. The problem is this resistor, of course, eats up power, and it really just all goes to waste. But again, looking at this 5,000 volt spike, we go, well, maybe there's some other way we could bleed off some power and use that to dampen this circuit, and I'm going to show you how that works right now. Okay, so I'm going to just redraw the tube so that we have a nice clear paper without all the other stuff on it. There's our tube. And again, what we're expecting to see over here is 0 volts most of the time, and then every now and then, as we do the flyback retrace on the picture tube, we get a spike that is perhaps around 5,000 volts. Well, what some very smart person did, and I don't know who they were, is they said, what if we took a diode and we put the diode here, and I'm going to say, well, we could draw it as a modern diode like this, but it could just as easily be drawn as a tube diode. Doesn't really matter. The bottom line is, if we have a diode here and we feed it into a capacitor and we have those 5,000 volt spikes and everything's up to those types of voltages, what we end up with is a 5,000 volt output over here that we can use for something else. And it's typically used for things like focusing the CRT. Well, that turns out to be bleeding off the right amount of energy at the right time to make sure that our output current is nice and smooth and is an almost perfect sawtooth waveform as we had hoped for. So that has now become the basis of our flyback converter. But you say, 5,000 volts, we need 20 kilovolts. Where does that come from? Well, that's actually pretty easy now, because what we do is we change this coil from just being a plain old coil to a transformer with a gazillion turns on this side. And if we were to connect the bottom of that coil down here, and we were to put a very high voltage diode, that tube in the high voltage cage over here, suddenly our 5,000 volt peak pulse over here is converted to a 20,000 volt peak pulse over here, and on the output of this diode we now have the 20 kilovolts that we use today. And that's really all there is to it. Now, these diodes over here, I've drawn them the modern way, but if we were going to draw them as tubes, we would just draw them like this. The circle representing the glass envelope of the tube, that's the cathode, and that is the anode or the plate. And the one thing that is kind of interesting is this diode up here, that's the one in the metal cage. It had that 1 volt filament, and depending on how you're doing schematic diagrams, you sometimes show the filament in a tube or not, because it's always understood to be there. Well, this diode here has a filament like that, and it needs to be driven with 1 volt, and all they did was take 1 loop around that same core of the transformer, and they used it to feed the filament down here. So it's really quite a slick system. What started off as a means for producing deflection on the cathode ray tube ends up producing 5,000 volts almost by accident to focus the tube, and 20,000 volts to drive the tube. Now, you might also be asking, but what about the deflection yoke? How are we going to deflect the electron beam back and forth if we turned this coil into a transformer? Well, that's easy. We just add 1 more winding to the transformer, and we attach that winding to the deflection yoke over here. So 1 transformer, 1 power output tube, and a couple of diodes, and we suddenly have horizontal deflection. On the picture tube, we have 5,000 volts that we can use for other things, and 20,000 volts to drive the picture tube, and that's actually a pretty slick circuit. And if you're looking at all of this, you might go, you know, that looks pretty familiar. And it actually is, because if you go back to a circuit that looks like this, with say a transistor down here, and a diode over here as an example, and this might be plus 5 volts, and we have a capacitor here, well, this could now be 12 volts if you wanted. That is the basis for some of the many switching power supplies that we use in all of our electronics today. So the switching power supplies we use today originated way back in the deflection systems of TV sets, probably 60, 70, 80 years ago, which is kind of neat. So that brings this video to an end. I hope you enjoyed it. See you next time.